Hello, and welcome to another live session in our online astronomy course. I know some of you are here live, and we got questions submitted by email, so I'm ready to start.
So I know everybody's excited to talk about gravity waves today, but I want to give other people a chance to join the chat. So we're going to ask a non-gravity wave question first, and then we will dive right into gravity waves. So the first question is from email. And the question is, is current string theory dead in its embryonic waters, or is there hope of further progress along these directions? How much effort is currently being expanded along this line of research?
It's a good question, and so actually quite a big question, because string theory has emerged in the past 20 years into a substantial field of physics, of theoretical physics. The short answer is that string theory is not dead. The reasons people got excited about string theory starting back to the early 1980s are still valid. Those reasons are that current fundamental physics is incomplete. The standard model of particle physics is incomplete, does not explain many things. The Higgs detection or the Higgs mechanism is an important piece of the standard model, but there's still profound mysteries about fundamental nature of matter. And string theory was designed to address them. The reason people got excited about string theory in particular was that it is mathematically and physically very elegant. It does, as we know, imply extra hidden dimensions that are only accessible on extremely large energies or extremely small scales of space. So those reasons and motivations haven't actually gone away. What happened in the interim was that, of course, the calculations and the development of string theory was extremely difficult. The techniques and tools have had to be made up by mathematical physicists as they go along, and only the very best physicists are able to do this. Also, the regime in which string theory might manifest its unique predictions is on such a high energy scale that it's inaccessible for most terrestrial experiments, certainly for accelerators or lab physics experiments. And that means that it's been subject to the criticism that it's not testable. And that's partially a valid criticism, and it's just the nature of the beast that you're dealing with something that's far beyond the realms of conventional physics. So because of all that, there has been a very visible and vocal backlash against string theory, and even some major physics department chairmen have lamented the fact that a whole generation of bright young physicists was drawn into string theory with essentially little chance of making substantial progress, and also for them, little chance of employment. Now, many of the best string theorists have been employed, and some are versatile enough to work on other things as well. But it's fair enough to say that the initial dreams of string theory have not panned out. And that's partly because it's a very difficult theory, and partly because of this gulf between prediction and observation. And really none of that has changed in the last 5 or 10 years. However, it hasn't been an overshoot. The string theory has not gone away. String theorists are still being hired. String theory is still being developed. And I guess the most important other thing to say is that string theory is not really one thing. It's turned out early on, actually, and it's been clear for a while, that there's a sort of network of interrelated mathematical and physical ideas that we now bracket under something called string theory. But there are many variations on string theory, many different aspects, and each of them to develop involves a substantial amount of work. So part of the problem is that even the currently reduced set of string theorists compared to 15 or 20 years ago is faced with exploring a really large number of possible theories. And that, in turn, has slowed down the progress because we don't know which of the variants of string theory is the most productive or fruitful.
All right, so with that, we will get to, we got 60 people joining us right now, and several people have similar questions. So if I don't call out your name, know that we are answering your question as well. So via email and from at least Jim online joining us, will gravitational waves be of use in studying dark matter? And I'm going to add dark energy because that's a question that people have.
Right. Not directly. Gravitational waves or gravity waves, I'm going to use those interchangeably. I was even taken to task online for using them interchangeably, but I think physicists don't really care about that distinction. It's understood what each mean. Well, we can use them both. They refer to perturbations or oscillations in space-time itself, in the fabric of the universe, propagating at the speed of light through space, caused by cataclysmic events for the most part. Dark matter and dark energy may be associated with the universe. Obviously, the universe is filled with dark energy, and dark matter makes up most of the composition of the universe. But gravity waves do not really directly reflect dark matter or dark energy. They propagate through a universe that's dominated by dark energy, but they don't allow us to diagnose dark energy. So the gravity waves don't hold any particular key to understanding dark energy. And similar is the story for dark matter, because as in the initial discovery from LIGO, these are massive black holes, and the material of those black holes is baryonic or non-dark matter material. So we're not looking at any gravity waves generated by dark matter here. So the short answer is no, gravity waves are not going to illuminate either the dark matter or the dark energy issues or problems.
All right, the next question is from our friend Alice Amanda. What new, exciting new things will we be able to discover and find using gravitational waves?
Well, the best and most exciting things are probably things that physicists haven't anticipated. Any time in the history of astronomy that we've opened up a new regime of observation, whether it's expanding the grasp of visual observation through the telescope or expanding the electromagnetic spectrum, as happened in the first part of the 20th century, or this even more profound expansion of capability by seeing the universe with gravity eyes, if you like, we found things that we didn't anticipate or predict. So I'm going to confidently and comfortably predict that the most exciting things that we will learn from gravity waves are not predictable or predicted or understood by scientists. That having been said, the LIGO experiment was, of course, pitched on the most likely things that it should have been able to detect, and merging black holes was top of the list. So hats off to LIGO for detecting the thing that they knew was out there and that they had the ability to detect. Some more exotic signatures that LIGO might detect are associated with the early universe and the Big Bang. But those signatures are not quite as characteristic. The black hole binary signature is such a characteristic, the chirp, as many of you have heard, it turned into sound form. That's such a characteristic and distinctive waveform in gravity waves that's very easy to filter out of noisy data. Some of the cosmic signals of gravity waves from, say, the early universe, the Big Bang in the first instance, are much more subtle signatures. They don't have that same characteristic crescendo and fall. And so they're going to be much harder to tease out of the data. And the scientists are barely started the business of trying to understand those. But there will be surprises, that's beyond doubt.
Great. The next question is from Vladimir, who is live on with us now. Could this amazing detection unify quantum mechanics and general relativity?
Not in and of itself. It's a part of affirming general relativity. It's a key prediction of general relativity that was in place not long after Einstein formulated the theory in 1916. In fact, Einstein, as has been documented, went backwards and forwards on whether the gravity waves that certainly are present when you solve the equations of general relativity actually were meaningful. He was unclear whether this physical phenomenon would really exist in nature. At the end of his career, he was sure that it should, and it's taken a long time to detect them. But this was a clear prediction of general relativity. So it's within the framework of general relativity that we understand gravity waves. And gravity waves in and of themselves have no reflection or reference to quantum scale phenomena. And so they're not going to help us with this grand unification that we're still seeking.
All right, the next question is from Maria, but then also Puneet online, who's on with us live. Does the recent successful detection of gravity waves increase the likelihood that evidence will be found that black holes emit Hawking radiation or emit radiation that Stephen Hawking predicted? That
would be great if that were the case. Unfortunately, no. To be clear about what the detection means, I mean, no, I haven't been asked that question yet, but at some point I'm going to say what the detection was and what it actually represents, because we're dealing with the big issues around gravity waves right now. The detection of this gravity wave signature, the simplest take-home, apart from affirming a key prediction of general relativity, is that black holes exist. They are real. This is the most definitive proof that we could want or have in science that black holes exist. Remember that until this time, the best evidence that the collapsed stages of massive stars form black holes is based on binary systems where one of the stars is a visible star and the other is inferred to be an evolved massive star with a mass of more than 3.5 times the mass of the sun. And by inference, that makes it a black hole. That's pretty indirect. It's good evidence, and people believe that black holes exist, but this is clinching it, because the only way that ripples in space-time could be propagated outward with that particular signature and that particular strength is from the binary merger of two massive black holes. A little more massive than most people expected for a first detection. So black holes have been proved beyond doubt. That's really a huge take-home of the LIGO detection. We should not doubt the existence of black holes. Hawking radiation is a different matter. Hawking radiation was a prediction from the 1970s that black holes actually have three properties. Initially, people thought they had mass and angular momentum because they were likely to be spinning. The third property from Hawking's theory is temperature. And if black holes have a temperature, then they're emitting a feeble amount of radiation. And the corollary of that, by conservation of mass energy, is that they're losing mass. So the prediction of Hawking radiation is coupled to the prediction that black holes evaporate and eventually disappear. Super long time scale for that. And the problem with Hawking radiation, super low temperature. I mean, we're not talking like a few degrees Kelvin, like the microwave background left over from the Big Bang. We're talking about nanokelvin, or actually nanokelvin is about right. So it's 10 to the minus 9, 10 to the minus 9, or 10 Kelvin. Tiny fractions of a Kelvin, and that is so far beyond the realm of detection by any astronomical method that most astronomers have just set aside the idea of detecting Hawking radiation for now.
So this is related to questions that we're getting, but I happened to walk by a talk that was being given here in the department yesterday about, or 2 days ago, about the detection, and I was amazed with all of the information we got from this single signal, things like this. Can you talk a little bit about what, like, all of the different things we know about these black holes that we detected from this simple signal?
Right. So it's one signal, and you've seen, I'm sure, the graph of the waveform detected with a few milliseconds time delay between the Washington and Louisiana versions of the same instrument, LIGO. The signal, the characteristic waveform, now the understanding of the signal is based on simulations, based on extremely sophisticated simulations in supercomputers that put black holes into the computer, full form general relativity, and of course encompassing the idea of gravity waves propagating through space-time. So the simulations that allow us to interpret what LIGO saw are extremely sophisticated and have only really been possible in the last 15 or 20 years. Matching what the signal was seen to the predictions of a supercomputer simulation allow the signature of the signal to infer the mass of both of the black holes, each individually, and the sum, and also the strength of the radiation. So there's the strength of the signal and there's the waveform. The waveform itself gives you the mass of the two black holes, they're individually, and the sum. The strength of the signal plus the way gravity waves propagate through space, essentially declining in strength with the inverse square law of gravity, gives you what is called a luminosity distance, where luminosity here means black hole, gravity wave strength, if you like, allows us to infer a distance, a luminosity distance, or a distance to the source of the gravity waves, and that's where the 1.3 billion years comes from. And so we know that these black holes merged in a very distant galaxy. That's not the edge of the universe by any means, 10% of the way to the edge of the universe, but very far away. There are tens or hundreds of thousands of galaxies closer than the galaxy where these black holes live. So we know it's very far away. From the time delay between the two signals and the order in which they arrive, we get a rough sense of direction of which part of the sky this galaxy 1.3 billion light years away was. But two LIGO experiments alone do not allow us to triangulate its position very accurately. So it's basically measured within a 60-degree patch of the sky. That's really big. That's just a big chunk of the sky. So we do know its rough direction, but we don't know its exact originating galaxy. We know the distance, we know the mass of the two individual black holes, and we also know from the luminosity or the emission of gravity waves that came out that another prediction of the theory is confirmed, which is that 3 solar masses of the combined mass of the individual black holes was released in the form of these gravity waves. And that, to many people, including many physicists, is a staggering consequence of these kind of phenomena, that in the merger and the reconfiguration of these two black holes into one, 3 out of a total of 60 solar masses of the combined black hole are essentially converted into space-time ripples with the strength that LIGO detected. That's an amazing thing, and that also is part of the theory. We've learned a few other more esoteric things, and actually they're still learning more, but those are the basics.
All right, Thomas, who I believe is online with us now, asks, I assume gravitational waves propagate in all directions, similar to a sphere exploding. If the universe is generally flat, how do the waves interact with objects in the universe and the void above and below their galaxy?
Right, that's correct. Gravity waves, if in a universe that's geometrically flat, space-time flat, and that's been measured by microwave background satellites, by WMAP and so on. So we do live in cosmically flat space-time. In a flat overall space-time, the gravity waves will indeed propagate according to an inverse square law of strength as you move out from the distance to the source. And that's how that distance to the source of these gravity waves at LIGO was determined. What is happening, of course, is that space-time itself is being slightly disrupted by a moving signal or oscillation that passes through the space in all directions. And that applies to everything within the space. So as this sphere, if you like, this expanding sphere of gravity waves, which in time sense has the profile of that chirp pattern, but is passing through every point in space, moving away radially from that distant galaxy, as those gravity waves pass across other galaxies, across stars, across planets, across, who knows, people in other galaxies, their space-time is subtly altered and feels that ripple. So that's one of the amazing things about gravity waves. Because it's space-time itself that's being altered, that alteration propagates at the speed of light across all the space-times between us and it, including all the galaxies between us and this distant galaxy. And of course, the Earth itself was affected, since the Earth sits in space-time. And finally, on the smallest scale, this test mass, what's called the test mass, which is this super pure, heavy bar of metal that's suspended exquisitely in the LIGO instrument to form part of an interferometer. Finally, that test mass was squeezed, if you like, by a distance that's less than 1,000th the width of a proton, and that was the signal that LIGO detected. But every piece of space-time between us and this distant galaxy suffered the same distortion.
All right, so several people have kind of a related question about the discovery. Since we have detected gravitational waves, this one is from Liang, sorry. Since we have detected gravitational waves, is it possible to detect gravitons, or what do we know about, like, what does gravitational wave detection tell us about the graviton, or the existence or non-existence of a graviton? That's
a good question, because our understanding of gravity is not complete. So that's an issue. General relativity contains a prediction of gravity waves, and as the term implies, we're thinking of them in wave-like terms. We're thinking of it as an oscillation in space-time. Now, gravity waves are a little different from waves, electromagnetic waves. Electromagnetic waves are transverse waves. They're electric and magnetic, sort of orthogonal electric and magnetic waves propagating through space, a vacuum or a medium, if you remember your electromagnetic theory. Gravity waves can be of that form, but they can be of a different form. They can be torsional, that is in twisting. They can be compression, and they can have a rotating vector. So in mathematical form, we call gravity waves tensor waves, which means they have a directionality, they have specific geometries, they have preferred directions. They're not as simple as a transverse wave, like electromagnetic waves. They're more complex, they have a much more complex phenomena. And so we have to understand them in those terms. As far as the graviton, but as you understand in physics, we have the wave-particle duality of light and electromagnetic radiation. So while we think of electromagnetic waves as waves with a wavelength and a frequency, we equally well think of them as particles, photons, and that's a 100-year-old physics. Well, also in gravity theory, we have always imagined that there's an analog particle to a gravity wave called the graviton, and it is the carrier particle for the force of gravity, as the photon is the carrier particle for the electromagnetic force. that's part of the standard model of particle physics. And so to answer the question, we've never detected gravitons. So we have not proved the existence of the particle analog of a gravity wave as we have many times and easily for a photon as an analog of an electromagnetic wave. Nor have we demonstrated that gravity waves propagate at the speed of light, as the theory predicts. That is actually an inference in this experiment. So it's important to be clear what LIGO detection did and didn't do. LIGO's detection did not show that gravity waves propagate at the speed of light. That's embedded in the theory and the interpretation and hasn't been tested. So the question is a really good one because we're still waiting for other types of experiments that will address the issue of the graviton, whether it exists, whether the signal, wave or particle, travels at the speed of light, and of course, in the end, what's a superior theory of gravity that helps us understand all this better.
So that actually takes us nicely to the next question, which we have from Adrian via email, which is how do we know the gravitational waves travel at the speed of light? But then also, can you talk about the stretching of space-time? Does it stretch faster than the speed of light? Why is it that something has to do with the same properties of the very same space-time that has a limit on its propagation speed? Like, how does this all connect?
It's really from the theory. So I'll again state it very clearly because it's important to distinguish things that are theory and things that are observed. We have never observed a propagating gravity wave to show that it moves at the speed of light, whether it's a graviton as a particle or the gravity wave itself. That is an inference as part of the theory, and that was not demonstrated by LIGO's detection. So we're, of course, therefore inferring, based on general relativity, that this signal was traveling through space for 1.3 billion years to reach us from a galaxy 1.3 billion light years away. That's an inference. That's not a direct measurement. So we're still waiting for a measurement that will show us the speed at which gravity waves propagate. Physicists, before LIGO even existed or was conceived of, physicists have been struggling for decades to imagine some lab experiment or experiment within the solar system that would allow them to show the speed at which gravity force propagates. So remember, this was a puzzle to Newton. So Newton was asked famously near the end of his life, what is this strange force of gravity that manifests across a vacuum and appears instantaneously to bind the Earth to the Sun and the Sun to the Milky Way and so on? And Newton gave the gnomic response, fingo non hypothesis. I don't frame a hypothesis. He didn't know. It wasn't part of Newton's theory. And it's not really part of Einstein's theory. What is the exact mechanism by which gravity waves propagate at the speed of light? So it's just considered a disturbance, if you like, in space-time. So if you imagine pure empty space as being linear space-time, the space completely linear and isotropic in every direction and time flowing linearly, then a gravity wave passing through it is just distorting the space-time grid. So you can imagine the grid of three-dimensional space marked by invisible dots that mark it out like points along a cubic lattice. So if you could just visualize that for a minute, a cubic lattice where those invisible dots are not really physical objects like particles, they're just markers, if you like, of space itself, something invisible. When a gravity wave passes through that space, those dots that we're using mentally to mark out space-time will shift around. And that's really what the disturbance of a gravity wave does. But because, as I mentioned, gravity waves are tensor waves, which have various modes of oscillation, those dots don't move in a completely simple way. They might move like a harmonic oscillator, sinusoidally up and down. That would be a standard transverse wave. But they might move in circular motions. They might move backwards and forwards like a compression wave, like a sound wave, or any combination of the above. So, but they're the same nature. You have to just imagine these dots that are invisibly marking space like a cubic lattice, all being moved around or shifted a bit as a gravity wave passes through. And it's that shift that LIGO was trying to diagnose with its instrument.
All right, the next question comes from Anna, who's on live. And she says, as mentioned in the course, LISA is supposed to detect gravity waves like LIGO with even more accuracy, but we only acquired results from LIGO. Why isn't LISA operating?
Yeah, so LISA is, well, first of all, the detection of LIGO not only cements LIGO as one of the greatest experiments of the 21st century in science, but also gives enormous momentum to the push to have LISA. So LISA was conceived of, maybe around the same time as LIGO, because there are things that LIGO can't do. So what are the limitations of LIGO? Let's just state that. LIGO is limited by two forms of noise, which essentially limit the frequency of these chirping patterns, or the frequency of these space-time oscillations that it can sense. The lower bound on the frequency is based on geological noise. They pick two of the quietest places in the US for geological activity. But even so, at a frequency of a few hertz or less than that, there's inevitable geological rumbling. Doesn't matter where you are, there is always going to be that. And so LIGO is not able to detect very, very low frequencies of gravitational waves. It also can't detect very high frequencies, because at that point the shot noise, or sort of photon or electron noise in the detectors, becomes significant, and that's a pretty hard limit. You can cool your detectors, you can do various things, but there's not much you can do there. The real problem for LIGO is that low frequency limit, because in the world of gravity waves, the mass of the objects that are either changing their mass or interacting or merging or doing something is roughly proportional to the frequency of the gravity waves that result. So the more massive the black holes, say, the lower the frequency of the gravity waves that result. So what the limitation on LIGO at the geological end of geological noise limits the mass of black holes LIGO can observe. Now, that's not a problem for stellar mass black holes, because LIGO, the sweet spot for LIGO, encompasses black holes ranging from a few times the mass of the sun, the lowest level of a black hole, to about 30 or 40 times the mass of the sun, close to the mass that was observed. So LIGO is going to be able to detect all the stars that die as black holes if they happen to be in binary systems. But now we know nature makes black holes all the way up to 10 billion times the mass of the sun in the center of galaxies. The one in our own galaxy is 4 million times the mass of the sun. So if you follow the scaling of frequency, black holes like that, which are either growing by merging or eating material, are going to have ringing, if you like, frequency oscillations in space-time, or gravity waves, that are very, very low frequency. We're talking about not just a few hertz or a fraction of a hertz. We're talking about millihertz or microhertz. That is one oscillation every 1,000 seconds or every million seconds. Extremely slow space-time oscillations. And there's no terrestrial experiment that can detect gravity waves with that low frequency. And that's what LISA was designed for. LISA is an acronym for Laser Interferometric Space Antenna. And it's basically a free-flying set of, in the original design, 3 Michelson interferometers. So the signal being combined between free-floating spacecraft that are exquisitely aligned, and the distance between them is measured to an exquisite accuracy, is essentially a LIGO in space. And because the space environment is so stable, and there's obviously no geological noise, no noise at all, you're in pure vacuum, far from the Earth, probably at a Lagrange point, LISA is able to detect these extremely slow gravity waves, which represent the action and activity and merger and growth of massive black holes that we know exist in the universe. So even at the time LIGO was being conceived and funded and built, people knew they wanted LISA as well, because we're going to not learn the whole story of black holes unless we learn about the massive ones. But LISA is a very ambitious, LIGO is an incredibly ambitious project. LISA is equally ambitious because it's LIGO technology, but it's executed in space with free-flying spacecraft. So the design studies for LISA were done in the 1980s, and the funding was clearly going to be in the multi-billion-dollar regime, which puts it into James Webb and Hubble Space Telescope category. It's a very expensive project. And it was so esoteric and so ambitious that, as you can understand, NASA always had higher priorities. As you can also understand, with LIGO succeeding, the motivation for LISA is now extremely strong. And so I think there's going to be a compelling case made, maybe not in the next few years, but within a decade or so, that LISA will be built. However, the politics has changed. You probably also read online that there's an experiment called ELISA, little e, with capital LISA. And this is part of the situation of NASA, where NASA really doesn't have a lot of money in its budget for new billion-dollar things, however exciting. And so the Europeans had separately, and the Europeans collaborate with the US on many projects like Hubble, like James Webb, and so on, But for a while, NASA's been in such hard trouble with its budget that the European version of LISA had more traction than the NASA version, was more likely to get funded and get funded quicker. So unfortunately, the way things are right now, it's possible that, you know, LISA will be built by the Europeans with minor US involvement rather than as originally planned as a NASA mission with minor European involvement. In the end, it doesn't matter. As long as one of these projects gets funded, physicists and astronomers will be happy. But they are very difficult missions. This won't happen for a decade at least.
All right, the next question is about the nature of gravity waves. This is asked by somebody who's on with us live. What is the biggest wavelength of a gravitational wave? Let's see, which is the biggest wavelength of a gravitational wave that can be produced by a phenomenon in the universe? Are there transverse and longitudinal gravitational waves? So, you know, talking about the wavelength and the
so the second part of the question, I've mentioned it indirectly already, that these are what are called tensor waves. So they have both longitudinal, transverse, rotational, torsional, all modes of oscillation that you can imagine in three-dimensional space occur with gravity waves, and all at the same time, possibly in the same phenomena. So they're very complex. They have a preferred direction. They're not sort of symmetric in the general case. So that's the first answer. We have to be sensitive to all the modes of oscillation that are possible, because the space-time can be oscillating and vibrating in all these different modes. And the wavelengths equally can be very different. Generally, the wavelength and the frequency are correlated, as they would be for electromagnetic waves. And with electromagnetic waves, the lower the frequency, the longer the wavelength. And the same is true of gravity waves. They are analogous in that sense. So the longest wavelength gravity waves that you were asking about correspond to the lowest frequency phenomena, which is the massive black holes. So the black holes that were observed in September, I was going to say a few weeks ago, announced a few weeks ago, observed in September, are releasing gravity waves that are millions of times or hundreds of millions of times shorter than the gravity waves that might be released when massive black holes collide in the center of galaxies.
All right, the next question is via email, and it is several people have questions about photons traveling at the speed of light. So this is shifting a little bit from gravity waves, but a photon does travel at the speed of light. So for a photon, 0 time and 0 distance has passed since the beginning of the universe. Basically, can you explain what a photon sees as its lifetime?
So the photon speed, the speed of light, if you like, in a vacuum, has been measured, was first inferred actually by Romer, a contemporary of Galileo, in the 1630s by very clever eclipse measurements of the moons of Jupiter. So we've known roughly what the speed of light was since the time not long after Galileo. And now it's measured with exquisite precision in the lab, because essentially we can do time of flight experiments with photons in the lab, and that we can measure a picosecond time delay. So we can measure light moving across a 1 meter distance. So the speed of light in vacuum or air or whatever transparent medium is really well understood with very high precision. So what happens in the universe, in space, deep space, the vacuum of space, where there's no medium, is that as measured by any observer, the speed of light as it leaves the observer is 300,000 kilometers per second in round numbers. And the speed of light as received by any observer in any apparent state of motion is also 300,000 kilometers per second. That statement, the constancy of the speed of light, regardless of the motion of the observer, is special relativity. That is Einstein's first great theory of physics from 1905. And that has been confirmed endlessly in the lab. We have moving sources of radiation where we can receive or emit the photons, and we always see that the arrival and departure speeds are 300,000 kilometers per second. And the consequence of that constancy of the speed of light, regardless of the motion of the observer or the recipient, is the foundation of special relativity, and the reason why we infer that mass is a supple quantity, that time is a supple quantity, and that length is a supple quantity. And the relationships of those three fundamental entities with speed relative to the speed of light is special relativity. It's just a set of equations that describe how they vary. Now, relative to the universe as a whole, we're in a slightly different situation because space-time itself is expanding. Slightly harder to understand is what happens to photons when they're traveling through the expanding universe. But if you take it down to the level of quantum physics and actually work through the quantum physics of this, what happens is that as photons are traveling through an expanding universe, their wavelengths are increasing according to the expansion of space-time. That sort of makes sense intuitively, because if space-time is expanding, then the distance between any two hypothetical points in empty space is increasing. And so a wave or a signal or a carrier of a signal propagating through that space will also have its wave or its distance between any 2 points expanding. And that's what happens if you work through the equations. So in expanding space-time, as light travels through space at 300,000 kilometers per second, as measured by any observer, as special relativity predicts, that those wavelengths are stretching because of the expansion of space-time. And that stretching is the redshift. That's what we mean when we say cosmological redshift in astronomy. And that has been demonstrated, endlessly, actually. So the theory of that is pretty well understood.
All right, so Anna, who is live with us now, would like to know if building an underground LIGO would give us better results for gravity waves.
Not necessarily, but it could. One of the LIGOs that's coming online, the European one that's next to come online, is in the Mont Blanc tunnel. So the Europeans have used a set of physics labs. They've had deep underground physics experiments operating in the Alps for decades, actually, because the Alps are kind of a mature mountain range that are geologically fairly quiet, and in most cases their physics experiments are there to shield from cosmic rays. So they're not really underground for reasons of geological stability, but for reasons of shielding from background sources of particle hits and so on. And so underground is in a good environment, but the truth is the geology effects that limit LIGO and limit any gravity wave detector, they don't go away or get better necessarily if you go underground, because geological disturbances propagate through rock and earth and so on very easily. So you don't immunize yourself from geological disturbances just by going underground. Really, all you can do and all you need to do is to go to the most geologically dull part of the world that you can find, a place obviously far from the Ring of Fire, the place where the tectonic plates meet, and that's easily satisfied, and a place where there's no mountain building going on, where there's no upwelling of magma that could be rupturing the crust or the mantle underneath you. You just look for the dullest geological places on Earth, and we have sensitive enough equipment now. People worry about earthquakes that are 5, 6, 7 on the Richter scale, but Richter is logarithmic, and so we have sensitivity to things that are 1 on the Richter scale or a fraction of 1 on the Richter scale, which is an absolutely imperceptible geological disturbance. So the equipment is so sensitive now that it's pretty easy to scope out places that are geologically quiet. And once you've found those locations, it really doesn't matter whether you're above ground or underground.
Okay, so Tom, who is again on with us live, would like to know, does the conversion of mass to energy in our sun cause gravity waves to be emitted from it? But then more generally, what causes gravitational waves to be produced?
Yeah, that's a good question. What causes gravity waves? In our sun, not directly. The conversion of mass into energy, which is happening continuously by the fusion process, does not in and of itself emit gravity waves. The outcome of that fusion process is the release of a flux of antineutrinos and a flux of high energy photons, gamma rays, in the place where the fusion occurs, and those photons degrade to visible radiation after 10,000 years of percolating through the sun and then travel to us. And that's a pretty steady process. So the key idea on gravity waves is that gravity waves result from a change in a gravity situation. Anytime a situation of gravity is not static but changing, gravity waves will be emitted. That's the simplest way to describe it. So the sun, as a stable star in the middle of its life, converting mass by fusion, is not really changing. It's a very stable object. Now, it is very subtly changing because as the sun ages and uses its nuclear fuel, it actually is slightly reconfiguring itself and burning a little hotter as time goes by. But that is such a subtle process and so steady and so slow that it's not going to make gravity waves. So gravity waves result from more dramatic changes in a mass situation. Now, that doesn't have to be a collision or a merger. So obviously, the most dramatic situations for gravity, if you're asking if gravity waves result from any change of a mass distribution or masses, then what is the most extreme thing you might imagine for gravity waves? It's the one that was detected. You take the most compact form of gravity, the strongest gravity field you can make, which is a black hole. You take two of them and you smash them together or let them merge. And so you've made the most cataclysmic change in a mass distribution that you can possibly make in theory. And that, of course, would be the first thing you would predict you could detect, or the easiest thing to predict by detect by gravity waves. And that's what we detected. Going down the scale a little is obviously lower mass black holes. The black holes that were detected are by far from the minimum mass of black holes. They're 25 to 30 times the mass of the sun. So if you took it down to the lowest mass black holes, 3.5 times the mass of the sun, same idea, but the gravity waves are a lot weaker. If you took a neutron star in a black hole and let them merge, gravity waves weaker still, because a neutron star is not as compact as a black hole. Two neutron stars would give you gravity waves, less again, because the neutron stars are less compact. And all of those are the things that LIGO is really looking for and expecting to see. But then you get into other things that LIGO might see. Supernovae, a dying star, is obviously a very dramatic and rapid reconfiguration of the mass of the star, which could indeed result in a black hole too, a single black hole. And that should emit gravity waves. Even more strongly if the supernova collapse is asymmetric. So if the supernova, for whatever reason, has an asymmetric collapse or an asymmetric explosion, that actually accentuates the gravity waves, because again, the gravity change is even larger. So we expect gravity waves from dying stars because of the cataclysmic effect. So, and those are that's the sum of the most likely sources that LIGO is going to see in the next few years, and probably has already seen some more that are going to be announced in the next months. Remember, we've seen an announcement that was an event that happened a few days before LIGO actually started taking science data, and it's now got 4 months in the can, so we should expect possibly a dozen more events. And anytime gravity changes, you could see gravity wave situations. So if you had a massive black hole in the center of a galaxy, like our galaxy, and it swallowed a star, yes, gravity waves would be emitted. So just basically go through the spectrum of astronomical phenomena and think of situations where mass is changing or gravity is changing. Then those are all gravity waves that could be seen.
And COVID has a question and is on with us live. And there are some assumptions built into the initial things. You may have to address those as well. The recent proof of gravitational waves shows that Newton's law is obsolete for velocities nearly equal to the speed of light. Can we say now that Newtonian gravity is only valid for Earth, general relativity is only valid for space, and vice versa? Is invalid?
I think we have to be careful about talking about the validity of these theories. The theories have regimes of applicability and regimes where they're not applicable. And so general relativity, when it was developed as a theory, did not, in a sense, invalidate Newton's theory or prove it wrong. Newton's theory is still the dominant theory of gravity to explain most of the phenomena of the universe, because in situations of weak gravity, it provides excellent, perfect predictions. All space travel in the solar system is conducted completely according to Newtonian theory. General relativity is not necessary. So, however, general relativity is a superior theory of gravity because in addition to explaining weak gravity regime, it also explains the strong gravity regime. So it's not like there's an area where Newton's theory works and then another area where it's useless, and one where general relativity works and the other where it's useless. Both theories are valid, but the regime of strong gravity, Newton's theory begins to fail. It does not contemplate, contemplate what's going on in space-time in a correct way, and general relativity is the theory. Now, we haven't yet encountered a regime where general relativity doesn't work. So no one has broken general relativity by any observation. It has passed every test put to it, and this most recent test is a very powerful test because it's in the strong gravity situation. Almost every test of general relativity for its first 100 years was a weak gravity test, where it makes slightly and subtly different predictions from Newtonian gravity, and the Einsteinian predictions were found to be valid. So general relativity is batting 1,000 at this point. It has never failed a test.
All right. The next question, I think, is very interesting about the relationship between gravity waves and the Higgs boson. Basically, does this prove anything about the existence of the Higgs boson? Like, how is the Higgs boson connected to gravity and to gravity waves?
Yeah, this is more subtle. I sort of said earlier that the gravity waves don't have a direct connection to dark energy and dark matter, and there may have been a little glib. There may be some subtle or profound connections between them. With the Higgs, it's less clear, and there may well be some very interesting connections. So to be clear, the Higgs particle, it's really a field to a physicist, or a mechanism, if you like. It's the mechanism by which mass is assigned to particles, by which we infer that particles have mass, that they're made of stuff, that they have inertia, and so on. And the Higgs effect, or Higgs mechanism, or Higgs particle detection a few years ago was an affirmation of the standard model of particle physics. So inasmuch as gravity waves reflect what happens when mass changes in the universe and how those signals propagate through space-time, and inasmuch as the Higgs field or mechanism attributes mass to entities in the universe, they must be connected. There must be some fundamental level at which they're connected. The simple answer is we don't know what that is yet, because what we're talking about is that same old thing that's come up several times now, which is reconciling quantum theory and gravity theory. So they are coming from different realms of our physical theories. The Higgs particle is an entity, it's the last entity that was sought in the standard model of particle physics, which is essentially the application of quantum theory to the very small phenomena, very small scales. And gravity theory is the discussion of the weakest force of nature that applies on very large scales through the universe. And so, yes, we think they must be connected, but to do so would require one of these overarching theories, not yet available to us, which unifies gravity and quantum theory.
All right, Amid asks, I lost the question. Oh, there we go. Will gravitational waves help us to know anything about the end of our own planet?
Interesting question. I think for a minute about that. Not particularly. I think gravity waves are, they're very subtle. Obviously, they're so hard to detect. They're really subtle. So that was a cataclysmic event. Two huge black holes sending out a cascade of gravity waves through the universe, reaching us 1.3 billion years later. And all it did was send a little ripple through space-time that was, far smaller than a proton. So if you think about the subtlety of that signal, then, it would take a huge, and you can imagine those black holes merging much nearer the sun. Let's just imagine they merge much nearer the sun in our own galaxy rather than in a very, very distant galaxy. The strength of that gravity wave signal would be vastly larger, maybe millions or billions of times stronger. But the truth is that the amplitude of it on space-time or on a human body or on the planet would still not cause any great disruption. So gravity waves are, because they're distortions of space-time and they are really quite small scale and subtle, they're unlikely to have any influence on the fate of the Earth. In fact, the fate of the Earth is basically governed by the death of the sun, which will flare out into a red giant in about 4.5 billion years and engulf the Earth with its outer envelope. That will be the end of the biosphere. And then the subsequent collapse to a white dwarf will render the sun dark or almost no energy, and then the Earth turns into an ice ball, and that's sort of the end of everything. Gravity waves won't have anything to do with this story.
All right, Doug would like to know, when the universe was created, all of gravity was in one point. So why didn't the universe immediately form a supermassive black hole?
Yeah, it's a reasonable point, because the universe in the Big Bang instant was like a singularity. It actually did have the characteristics of a black hole. It, in a sense, had an event horizon, but that event horizon contained all the stuff that would eventually form 100 billion galaxies. So it's a good question, and I guess the answer is that since as we observe ourselves in an expanding universe, we can infer that the energy of the expansion is larger than the gravitational binding energy associated with all the mass in the universe, and that's sort of essentially what we measure. So the universe was in a dynamic situation where it was going to continue to expand and thin out, and so very quickly moving away from being the description of a black hole.
All right, the next question is from Mike, who would like to know about the Planet 9. He has a question about Planet 9, which is another recent story in astronomy, and we have about 5 minutes left. Referring to the alleged 9th planet discovery by CalTech, have they worked out an actual orbit, round or oval, or will this take years of observing to determine that?
No, they have not identified Planet 9, as it's being called. It's under active investigation. It's possibly bubbling under the surface as a discovery that we haven't heard about yet, like the gravity wave discovery that was under the radar for several months. No, it's detective work. The sort of orbits of smaller objects in that region of space that infer the existence of Planet 9 and its mass do not localize it extremely tightly. And so now it's just hard legwork with medium-sized telescopes. Don't need super large telescopes, but they can't be small as a meter. They're a couple of meter-sized telescopes, and a network of them just trawling, strip mining that part of the sky, which is a substantial part of the sky, to find a moving object, reflecting a feeble amount of light because it's so far from the sun in the Kuiper belt, and then measuring its mass and eventually finding that it's Planet 9. So that is going to happen, and the people involved in this work are giving it a couple of months. They really think they could get lucky. It could happen next week. You could search an area of sky and you could find it in the first 10% of your search and be lucky. But on average, it's going to take a month or so.
Okay, so the last question that I think we will take for today is from Jose. And the question is, could gravity waves be used to transfer information? Do they travel larger distances than electromagnetic waves?
That's a good question. Good question to finish with. Yes, in principle, gravity waves could be used to carry information. And the second part of the question is really interesting because they are excellent information carriers. Because if you think about it, think about light, think about electromagnetic radiation. Light, most forms of electromagnetic radiation don't even make it through the Earth's atmosphere. It's opaque to them. Most forms of light don't make it to us from the center of our galaxy. Only infrared and radio waves do. So large parts of the universe, deep space, of course, intergalactic space, light and electromagnetic waves travel freely, but a lot of forms of electromagnetic radiation are absorbed, scattered, deflected, or extinguished by traveling through a galaxy or an atmosphere. And so gravity waves are immune from all of that. They essentially propagate, because they're ripples in space-time itself, they propagate through space-time regardless of the objects in their way. Galaxies, stars, planets, people, doesn't matter. That was an earlier question asked that. So they're brilliant information carriers if you could harness them. And so to get back to the first part of the question, what would that take? So at the moment, we're stuck with LIGO observing natural gravity waves produced by stellar cataclysms in the universe, emerging black holes, for example. In principle, if we had the technology to do it, if we could orchestrate mass changing dramatically on different scales, we could generate gravity waves ourselves. Now, we may never be able to manipulate mass at the level of stars. In other words, fabricate black holes and crash them together. If we could, we'd generate gravity waves. Perhaps we can do that on a substantially smaller scale with miniature black holes that would create the fusion processes like the lasers at Los Alamos that are used to create controllable fusion. So it is conceivable that if we could harness a mechanism to create very small compact masses or change compact masses, we could imprint information in the form of a gravity wave that would then propagate seamlessly through the universe. So I'm going to guess, as my final thought, that advanced civilizations, far cleverer and more sophisticated than us, have learned how to do this. And they would look at our electromagnetic communication and say, oh, how 21st century, because they in the 23rd or 24th or their 30th century of technology have developed the ability to harness gravity waves, encode information in them, and send them seamlessly through the universe. And maybe they're already talking to each other this way, and we just don't know about it.
So we did have a lot of visitors today and a lot of questions that we didn't make it to today. So I would like to thank all of those people for asking and say, join us again next time. We were so dominated by gravity.
Right, and we will revisit this, and I will make an apology that we are taking a slightly longer hiatus than usual. We like to do this every couple of weeks. You don't need to cry for me, though. I'm going to Indonesia on Wednesday to watch the eclipse in Borneo on the day of the eclipse. So we're taking a few weeks off, but we'll definitely be back online after a few weeks. Okay, thank you and goodbye.